Hey everyone, and welcome. Today we are going behind the curtain on one of the most powerful AI models out there. And we're not just going to talk about what it does, we're diving straight into the source code to see how it actually, well, thinks. So, let's just start with a huge question. When you try to picture the mind of an AI, what do you see? Is it one of those crazy diagrams with a million glowing lines? Some kind of pulsing orb from a sci-fi movie? The reality, it turns out, is a little more down to earth and, honestly, way more fascinating. Because get this, it looks like this. It's not some abstract concept, it's just code. Structured, kind of elegant Python code. This right here is the architectural blueprint for an artificial mind. And in this explainer, we're going to walk through this blueprint, piece by piece, and really understand how these lines of code create something that can write and reason and even create. Okay, let's dive right in. Here's the game plan for how we're going to deconstruct this thing. We'll start big picture with the overall blueprint. Then we'll zoom in on the most important parts, the core units that do all the work, how it pays attention, how it understands word order, which is so cool, and how it uses a team of experts to think efficiently. And then we'll put it all back together and see how this code really does become a kind of cognition. All right, first up, the big picture. You see, everything inside the Llama model is held together by one master class called the transformer. The best way to think about it is like the main chassis of a car. It's the frame that holds the engine, the wheels, all the essential parts right where they need to be. So this transformer class, it's the master controller. As soon as the model boots up, this is the code that initializes absolutely everything. It creates the token embeddings, which is really just a fancy way of saying it turns the words you type into a language of numbers the computer can actually understand. And, crucially, it builds the stack of processing layers where all the real thinking is going to happen. So how does a piece of information actually travel through this thing? Well, it's a pretty clean four-step journey. Step 1, your words get turned into those numerical vectors we just talked about. Step 2, those vectors get pushed through a whole stack of processing layers. Step 3, a final normalization step, using something called RMS norm, kind of cleans everything up. You can think of it like a sound engineer, tweaking the levels to make sure the signal is perfectly clear and stable. And finally, step 4, the output layer takes that beautifully refined vector and predicts the next word. It's really an elegant and powerful flow. So if the transformer class is the car's chassis, what's the engine? Well, that would be the transformer block. And maybe a better analogy is the engine's piston. It's this core repeating unit where all the heavy lifting, all the computation happens. The entire model really is just a big stack of these blocks, one right after the other, with each one refining the model's understanding. And each one of these transformer blocks has a really clear two-step job. First, it uses something called an attention mechanism to figure out which words in a sentence are the most important right now. And second, it uses a feed-forward network, which is basically a bunch of math, to think about the information it just gathered. And it just does this over and over and over again. So let's dig into that first step inside the block, attention. Now this is, you could argue, the most magical part of a transformer. The best way to think of it is like a dynamic spotlight that the model can shine on the text to decide exactly which words to focus on in any given moment. The attention class is what makes this happen. For every single word, it creates 3 special vectors, a query, a key, and a value. Now think of it like this. In this sentence, the cat chased the mouse because it was fast. The query for the word it is basically asking a question like, hey, what does it refer to? The keys for cat and mouse then respond. The model calculates how well each key matches the query, and here mouse would obviously get a much higher score. And those scores determine how much of each word's value, its meaning, gets passed along. It's just a really sophisticated way of weighing the importance of every single word against every other word. But there's a big problem. Standard attention, on its own, just sees a sentence as a bag of words. It has no clue about the order. And for language, that's a huge issue. So Llama uses this incredibly clever solution called rotary positional embeddings, or ROPE for short. I mean, just look at how critical this is. Without knowing the word order, king kills queen and queen kills king are exactly the same thing to the model. The meaning is totally lost, right? It's a mess. But with rotary embeddings, the model suddenly gets the sense of sequence, and the meaning becomes crystal clear. And the little piece of code that pulls this off is this secret sauce. This one function, apply rotary m, is the whole key. Right before it calculates attention, it takes those query and key vectors and literally rotates them. The amount it rotates them depends on the word's position. So a word at the beginning gets a tiny little rotation, a word at the end gets a much bigger one. This embeds the positional info directly into the vectors. It's like giving every word its own personal GPS coordinates. It's a brilliant move because it's super efficient and works great even for really long sentences. All right, so after the model has used attention to gather all the important context, it has to actually process that information. This is that second step inside the transformer block. And here, Llama actually has two different ways it can think. If you look at the code, there's literally an if/else statement. The model can either use a standard feed-forward network, which is kind of like one giant superhighway that all the data has to travel on, or it can use what's called a mixture of experts, or MOE layer. Now, this is more like having a bunch of smaller specialized workshops. The model has a router that actually learns to send each piece of information to the expert best suited to handle it. Maybe one for coding, one for poetry, another for historical facts. It's a much smarter and way more efficient way to expand the model's knowledge without skyrocketing the cost of computation. So now let's zoom back out and just see how all of these incredible modular pieces of code snap together to create a complete cognitive engine. So here's the crucial takeaway. What looks like this incredibly complex AI is actually a beautiful assembly of really well-defined parts. You have the transformer acting as the chassis. You have the transformer block as the piston, firing over and over and over. Inside that piston, attention is the spotlight, apply rotary M is the GPS, and the MOE layer gives it those specialized processors. And things like RMS norm, they're the stabilizers, making sure the whole engine runs smoothly without overheating. Every single part has a very clear job. We've just walked through the entire architectural blueprint of an advanced AI, and hopefully you see that it's not some unknowable magic. It's a system, a really clever one, but it's built from understandable parts. And seeing the code this way as a set of building blocks, it kind of changes how you think about it, doesn't it? It's not just a static object to be used, but a blueprint to be understood, to be modified, and to be built upon. So I guess the final question is, now that you've seen how it's made, what would you build?